So for that we introduce F mu nu, a 4 tensor, antisymmetric 4 tensor. F mu nu is equal to minus F mu, and they are related to our well-known fields in the following way. F0I is the same as the electric field, I going from 1 to 3. F0I is minus Fi0. Fij, which is the same as F minus Ij, is epsilon Ijk, the usual Levi-Civita tensor, antisymmetric tensor. So that gives magnetic field, that gives electric field. And Maxwell's equations. C I am always putting as 1. Faraday's law of induction and Gauss' law for magnetism and Ampere's law. I think it is the other way. This is plus. Please check all these things. I might have missed the signs. Equal to this Ampere's law. These are Maxwell's equations, and Maxwell's equations can be rewritten in terms of this relativistic notation. It all the 4 collapse into one single equation, d mu F mu nu. Here I lower, because whenever we contract, this is called contraction. This is called contraction. One has to be lower, one has to be covariant, one has to be contract. This means d by dx mu. This means d by mu above. That means I differentiate with respect to the covariant. That is the meaning of. Okay. D mu F mu nu is equal to J nu. So all of Maxwell's equations become like this. J nu is the 4 current, so J0 is nothing but the charge density, and then there is Ji. So J mu is equal to rho and Ji. So all of Maxwell's equations can be elegantly written as just in one line. Then we introduce the potentials. This is all just a revision of electromagnetism. It is good to do it again and again so that it becomes second nature to you. Potentials, electromagnetic potentials. E is equal to minus gradient of a scalar potential plus dA by dt, whereas B is simply the curl of A. Again, in relativistic notation, the whole thing becomes F mu nu is equal to d mu A nu minus d nu A nu. Please verify all these things. Show that from this you can get these things. So we have introduced the 4 vector potential A mu, which is the usual scalar potential and the usual vector potential. I think that's all I have to say. Now let us go to the quantum mechanics of particles. Of course, you could start with Schrodinger equation, but that is not relativistically invariant, so I will not do that. Instead of that, we straight away go to the Dirac equation. I have already said some things about Dirac equation, but now let me say a little bit more. Relativistic equation, relativistic wave equation, namely Dirac equation. I gamma mu d mu minus m or plus m, I do not remember, into psi equal to 0. These are 4 by 4 matrices. gamma 1, gamma 2, gamma 3, gamma 4. I am sorry, gamma 0, gamma 1, gamma 2, gamma 3. There are 4 of them, and they are 4 by 4 matrices. And each entry in the matrix is only a number. It can be given like polymatrix. These are sort of generalized polymatrices actually. That is how Dirac constructed them. And they are matrices, so they don't commute. In fact, they satisfy anti-commutation relations, gamma mu. Let me overwrite. They also can be lowered or raised. So that is this, or you can write G x mu equal to G mu nu x nu, and G mu nu also, G mu nu with both above, both below, both are the same metric tensor. It's called metric tensor. Gamma mu is equal to same G mu nu comes here. In fact, this is the defining. That's all. Gamma 4 matrices, 4 by 4 matrices satisfy these are called the Dirac matrices, and they play an essential role in Dirac equation. And let me now go to the Lagrangian. Let me write down. I don't know whether I wrote it down earlier. Lagrangian for the Dirac field. That's all. If you write down the Euler-Lagrange equation for this Lagrangian, which will involve differentiating this with respect to psi, as well as differentiating this with respect to the derivative of psi and equating them. That is Euler-Lagrange equation. And from the you can show. So del by d psi is equal to d by dx mu of I have written a curly L because they are actually Lagrangian densities. Lagrangian density divided by differentiation of with respect to this derivative, let us say d mu psi. This is Lagrangian density differentiated with respect to the derivative of psi and then differentiate it, and that should be equal to this is Lagrangian. Do this as a simple exercise and show that from this follows. It can be done. Actually, you can do it either with respect to psi or psi bar. If you do it with respect to psi bar, you will get this equation. If you do it with respect to psi, the corresponding equation for psi bar will come. Okay. Now, what is quantum electrodynamics? That is the Lagrangian just for a free Dirac field. This is the free Dirac equation. But quantum electrodynamics is electrons interacting with electromagnetism. So let me write down the Lagrangian for this. It will be this minus 1 over 4. I could have done one more thing right here. In free space, that means there are no currents or charge densities. Then the Maxwell's equation is simply d mu f mu nu equal to 0, and this can be obtained as the Euler-Lagrange equation from this Lagrangian. So this is the Lagrangian for Maxwell's free Maxwell's theory at least. So Lagrangian is equal to minus 1 over 4 d mu f mu nu. So two indices are below, here two indices have to be above before they can contract. So this is the Lagrangian density. The Euler-Lagrange equation for this will give you this Maxwell equation. Okay. That is quantum electrodynamics in free space. So now let us consider couple the Maxwell's field, electromagnetic field, with the charged electron described by the Dirac equation. So you will have minus 1 over 4 f mu nu plus the Dirac Lagrangian. Plus the interaction coupling term. How come I did not write? Now you know how to write down the coupling term. Let me rewrite it in a slightly different way. Psi bar gamma mu I. D mu has to be changed to d mu plus I E. E is the electric charge on the electron, A mu into psi. That is how interactions are generated. All derivatives are replaced by the so-called covariant derivative. Covariant with respect to gauge transformation. I am going to talk about that. Anyway, I don't use that notation now. I mean that word now. I have not defined gauge transformation. I have not described gauge transformation so far. I am coming to that. Yeah, I think I should stop now. So d mu plus IE A mu. So this is the quantum electrodynamics Lagrangian. Free Maxwell field and free Dirac field plus the coupling term, which is A mu into psi bar gamma mu psi, basically, which is the current. Current into the vector potential is that. So when I said Euler-Lagrange equation, I should have noted down one thing. In that, it is not the fields which are used, it is the vector potentials which are to be used. Euler-Lagrange equation regarding A mu as the canonical variables, and the I mean, you have to write down Euler-Lagrange equation with respect to A mu and its derivative, not with respect to fields. Fields become derived objects in electromagnetism. As I already mentioned, it is the potentials which play a primary role in electromagnetism, especially in quantum mechanics. Okay. Similar Euler-Lagrange equation with respect to A mu, namely you will put a mu here, and then let us call it A nu here, and here d mu A nu, and that will give you the Maxwell equation. Even the full Maxwell equation with J nu will come now because interaction term has been put. So let me give that as an exercise. Derive d mu f mu nu is equal to J nu as Euler-Lagrange equation. Euler-Lagrange equation. So that is quantum. That is not QED. That is electrodynamics. We have not come to quantum electrodynamics. QED partly because I mean the particle is described by a wave function, so let us not call it quantum electrodynamics. It is you can say particles treated quantum mechanically, but the electromagnetic field treated as a classical field. That is this Lagrangian. Okay. I will make one or two remarks since we lost some time. Is it okay? Some 5 minutes shall I take? Hello? Hello? Satya? Again we have lost the connection or what? Hello? Joseph, can I take another 5 minutes? Yeah, because we lost some time today. So let me just go ahead. Some gauge transformation has to be mentioned. Here we can take it up later. The point to note is, look at this Lagrangian. First, look at the phase transformation. This Lagrangian is invariant under the transformation psi goes to psi prime, which is equal to e power I alpha into psi. Psi and psi prime are functions of x, but alpha is a constant, any arbitrary real constant. Under this is trivially invariant because psi bar, remember psi bar is basically Hermitian conjugate. In all these things I should have said psi bar is Hermitian conjugate times one of the gamma matrices, namely the zeroth component. That is the definition of psi bar. Psi bar will be constantly being, it is like a complex conjugate or Hermitian conjugate, but it is this which really comes everywhere. Since psi bar has complex conjugation, that will go as e power psi bar will go to so you can see it is trivially invariant because psi bar and psi always come together. So this is constant phase transformation. But now to make it into a gauge transformation, consider psi going to psi prime equal to e power minus e power I alpha function of space time by x means x mu, all the components will come. Under this also it is invariant. Where alpha x is x dependent. Under this also no, this is not enough. Now what happens is the mu also has to be transformed. Let me get it right. Mu is equal to mu plus 1 over E into d mu alpha. If simultaneously both transformations are made, you can show that because derivative is there. Since derivative is there, there is a derivative of alpha will come, but that gets compensated by this. Please show this where alpha x is x dependent. L, this L is invariant under this combined transformation. This is the most important statement. This is called gauge invariance. This is actually the gauge invariance of original electromagnetism, because this transformation you can easily see is the gauge transformation, usual gauge transformation. You can reinterpret it in terms of the spatial part of it, spatial vector A, and the scalar part phi. So this is nothing but the usual electromagnetic gauge invariance, but that is accompanied by a space-time dependent phase transformation on the charge bearing field. Any charge bearing field has to be transformed like this when electromagnetic potentials are gauge transformed. So this together is called the gauge transformation. Lagrangian is invariant under a x provided the vector potentials also transform by the derivative of the same phase vector. Okay. So that is the most important thing. I will take up, I have to say something more interesting about this line of development after. So please verify this. So this is an exercise again. Show this. This is a very simple exercise. Show this. Again, about the signs, I am not very sure whether I have to put a plus or minus. You have to choose the sign appropriately depending on the sign here, and I might not have done the signs correctly. Anyway, it is doable. Please do that. I think I will stop there. I will now generalize this. This is called abelian gauge transformation, because this is actually abelian. This phase transformation is also called U1. It's unitary. I mean, this into its star is 1, so it is unitary, but actually it is a number. one-dimensional unitary matrix. So it is called U1 transformation. This